8 years ago, I decided to create a world record with a tiny LoRa transmitter. The distance? 202 kilometers. Today, I'm trying something even more ambitious, with this small ESP32 module. Its Wi-Fi range usually covers just our home or maybe 50 meters around it. But this time, the goal is far more extreme. Can we send its signal 36,000 kilometers? That is nearly once around the world. If I'm successful, I'm pretty sure this record will be valid for a long time. The race is on. Grüezi YouTubers, here is the guy with a Swiss accent, bringing you a new episode with fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you'll always sit in the first row. For this world record, we need two things. This ESP32 module as a transmitter and a receiver at a very long distance. Of course, the key requirement is a line of sight between the transmitter and the receiver. That's easy for flat earthers. But for the rest of us, we need a receiver in space. Fortunately, I have access to one. Frequent viewers know I'm a ham radio operator. This gives me access to a geostationary satellite located 36,000 kilometers above Earth. It's called QO100 and it covers the area from Brazil to Pakistan, including Antarctica. Sounds like we are good to go, right? Not so fast. Satellites use an uplink and a downlink. Let's have a look at the QO100 band plan. Its uplink frequency is in the 30 cm ham radio band, which, by coincidence, is just below Wi-Fi frequencies at 2.4 GHz. Its downlink frequency is in the 10 GHz range. We have to comply with this band plan, so we will have a closer look at it later. Knowing that, we have two major technical hurdles. Get the ESP32 to transmit on the correct frequency and ensure the signal is strong enough to bridge the 36,000 kilometers. Both are challenging. Why? First, the standard ESP32s only transmit Wi-Fi signals above channel 1 or 2.41 GHz, outside QO100's uplink range, which is from 2.4 to 2.4005 GHz. And second, the chip's maximum power output is only about 20 dBm or 100 milliwatts. That's not much to reach space. For a long time, there was no solution to create appropriate frequencies. The Wi-Fi firmware is closed source, and Espressif didn't want to support anything they considered illegal. But then I stumbled upon a presentation by a few young hackers at the Chaos Computer Club event in Berlin. They had reverse engineered Espressif's code, at least for the ESP32 C6, and could generate signals in this frequency range. You can imagine my excitement. This suddenly made my project possible. Assuming their code works, what modulation should I use? Wi-Fi won't work. Its bandwidth is both illegal on the satellite and unsuitable for such long distances. But there is a very old digital modulation that works with very weak signals. Morse code. Morse is simple to generate and decode, especially if you worked as a radio operator like me when I was young. So this could be the path forward. Unfortunately, there is still the issue of power. And as you'll see later, it's even worse than expected. First, let's talk about my setup to reach the QO100. I use a 1.2 meter dish antenna on my roof aimed at the satellite. Such antennas give a gain of around 25 dB on 2.4 GHz. That's about 300 times amplification. If we multiply the 100 milliwatt by 300, we get 30 watts. Not bad for such a small device. But will it be sufficient to bridge the 36,000 kilometers? The downlink offers even more. Because it is on a higher frequency, its gain is around 40 dB or 10,000-fold. This is why we can watch TV across this distance. So there is hope, but now we need to focus on the ESP32 itself. The hacked ESP32 code is experimental, low-level and not well documented. It runs only on the ESP IDF framework and even then only on version 5.2.1 with a special patch. After quite a bit of work, I managed to get it going. If you want to try it, I've uploaded my code to GitHub with lots of comments. You just have to patch the ESP IDF, change the call sign and upload my code to a C6 module. For hardware, I used this CAO board, the only ESP32 C6 module in my lab with an antenna connector. An interesting detail: most boards with an antenna connector require soldering to switch between internal and external antennas, not the CAO. It has a built-in switch that you can toggle using a GPIO pin. Neat. Will it work? I choose this frequency for my signal. That falls within the Morse part of the uplink band. If I power the board, we can see the Morse rhythm on the spectrum analyzer at the proper frequency. Time to fire up the SDR receiver for the QO100 and connect the CAO module to the antenna on the dish. We see and hear other satellite signals. So the receiver is working, but nothing from my CAO. The experiment fails. But I don't give up easily. Back at the spectrum analyzer, the problem is obvious. The output power on the external antenna is just 4 dBm or 2.5 milliwatts. Nowhere near enough to bridge 36,000 kilometers, even with a dish. This could be due to the ESP32 working in an unsupported mode, or maybe just poor board design, especially the antenna switching system, which may reduce the output power even more. I tried a second CAO board with the same result. Espressif has a special RF certification tool for testing modules. It can generate a tone at a fixed frequency, great for testing. The result? Even more disappointing. Only 0 dBm output. And the tone is unstable. The frequency drifts quite fast. Not good for Morse. But then I realized this measurement is completely wrong. I wasn't measuring the output of the external antenna, just crosstalk from the internal one, because I couldn't switch the GPIO for the antennas in this test mode, and by default the internal antenna is selected. So we have to use the measurement of our hack. 4 dBm is the real number. For reference, this is an old ESP32 with an internal and an external antenna without instructions on switching. Still, it gives me around 14 dBm or 10 times more power than the CAO. At least something. And its frequency is stable too. But unfortunately on the wrong frequency because I do not have a hack for it. To compensate for CAO's weakness, I add a 10 dB amplifier, bringing the total output to about 13 dBm, roughly what a typical ESP32 should be able to deliver. I connect this setup to the dish antenna and try again. It is quite weak, its sound is bad, and the frequency isn't stable. Still, we clearly hear test the HB9 BLA. We did it! We proved we can bridge 36,000 kilometers with an adequately mounted ESP32 chip, using only 15 milliwatts of power. I was hoping the Xiao would perform better, but I'm not giving up. I've ordered another module, this time from Espressif, with only an antenna connector. The module itself has nearly the same size as the Xiao. I had to replace the standard module on this development board for the test. Let's check its power. Also not the promised 20 dBm, but at least 8. So if I adjust my antenna to the max, it should work without an amplifier. And really, here you hear and see the world record with your own eyes. The signal is clearly visible above the noise floor. Of course, I have to adjust the frequency, but the signal of the Espressif board is more stable, a sign for a better oscillator. Now I can get a beer and celebrate. Want to hear these signals yourself?
Perturbazione passi, questo ci lasci un pochino divertire per quanto riguarda le vacanze passate. Ti restituisco il microfono.
You don't even need a dish antenna or a receiver. Just go to this website and you can listen in. You might even catch the signal from an ESP32 module like mine. How cool is that? One last thing. Because this Xiao board's Wi-Fi performance was so poor, I decided to order all available mini boards to create a comparison video. Will the others be better? That was all for today. As always, you find all the relevant links in the description. If you found this video useful or interesting, please support the channel. Thanks for watching and see you in the next video. Bye!